Okay, so this lesson's for Friday, November 11th, 2011. Today we're going to be taking some notes. You might have noticed as you walked in that there was some Cornell note paper. You'll want to go ahead and pick that up. And as we go through these notes, it'll be important that you fill in those notes on your own paper the best that you can. The Cornell notes, remember, on the right-hand side of the Cornell note paper will be where you write down any detailed note-taking about the PowerPoint, and on the left-hand side would be where you would include any questions or the main ideas of what's on the right side of that paper. So as we go through this, if you do have questions about that, I'll be walking around the room. You can go ahead and ask me, and I'll be happy to help you with that. Again, on the website, the weekly agenda, there's a section right here in the link section for the notes. So if you click on that, it will take you to the work and energy notes. Let's just go ahead and get started with these. Your topic for the notes is going to be work and energy. You'll want to put that at the top left, where you always do. Today we're going to make sure that we define work, we're going to define energy, we're going to describe a relationship between work and energy, and we're going to define power and relate it to work and energy. Really important that you leave with this main idea and that you understand it, that work is just basically the transfer of energy that occurs when you apply a force over a certain displacement. So make sure that you're really clear on that as we go through this stuff. All right, so you'll recall that when we talked about forces, we talked about a system and how the system is going to be the object of interest and everything else that interacts with it. So it's going to be really important that you remember that as I talk about forces in the system and the forces that are involved. Okay, it's going to be important also that we identify the variables that are responsible for creating work. So force is one of those variables. Remember, force is measured in newtons. And we're going to look at how that force is applied over a certain distance. And that's going to be a variable d that you'll see in the equation here in just a little bit. And work is going to be the new thing we're talking about. Will be shown with a capital W in the equation. You're going to need to know that the unit for work is a joule. The SI unit for work is a joule. And that joule is equal to 1 Newton meter because we're multiplying a Newton times a meter. That's where the unit comes from. Okay. The equation for work is work equals force times distance. So it'll be important that you write this equation down. It's just the product of your force and an object's displacement. It's important that you know that if a force is exerted perpendicular to the direction of the motion, then the work done is 0. What I mean by that is that if the object's motion is to the right, so this is the motion of the object, but the force is put on the object upwards, so if this is a force, sorry about drawing in the middle of the paper, then the actual work that's done would end up being 0. That's important that you understand that. The force has to be in the direction of the motion for work to have occurred. If it's perpendicular, which means if it's at a right angle to the motion, then no work has been done. And that's going to be important. Okay. You'll notice down here that there's another equation, work equals force times distance cosine theta, where theta is an angle. This is only an equation you'll use whenever there's an angle, so that the force is put on an object at an angle in relationship to the motion of its direction, wherever it's going. So we'd only use this equation if there's an angle involved. And we're not going to really get to this till a little bit later, and I'll actually show you some word problems where we talk about that. Okay, so there's a lot of different ways that you can calculate force. You can calculate force by, using the equation that we just talked about. It's going to be important that whenever there are several forces on a system, that we calculate the work done and then add the results afterwards. So we'd add all the forces, all the work done afterwards. It's also important that you understand that the direction of the force is very important. Like we just talked about, if it's at a perpendicular to the motion, that would mean that that force would be contributing no work to the object. The graphs for force versus displacement, you'll see 2 graphs down here. We can get the area under these lines, and that actually gives us the amount of work done. So for objects where you have a changing amount of force, so you can see that the force here is changing, whereas the force here is constant, For objects with changing force, instead of using the equation W equals Fd, because the F is changing, we can actually do a graphical analysis and just get the area here to get the amount of work done. So this is an option whenever you have a changing amount of force. We would use the graphical method to solve those problems. Okay, so this is an example where that would be important. They've given you a graph, and because you have two areas on this graph where there's changing amount of force, right here and then right here, we would actually go ahead and get the area here, where you'd get the area of this right triangle first, then you could get the area of this rectangle, and then the area of this rectangle right here, and then the area of this final triangle that's made at the top. And we'd add all those works together to get the total amount of work done over this 10-meter distance right here. Okay. Again, we would just use the equations for a triangle, which is 1/2 base times height, and then for the rectangle and the squares here, we would use length times width, just to add everything together. Okay, so let's take a look at an example problem. It says a hockey player exerts a constant force of 4.5 newtons forward to a 105-gram puck sliding on an ice over a displacement of 0.15 meters forward. Let's go ahead and highlight that forward part. And they want to know how much work is done by the player. Okay, so we've got our givens and our unknowns there. The first thing that we have for our given is the force, so this 4.50 newtons. We have a mass right here, but it's in grams, which is important. We want to convert that into kilograms. And then we have the displacement over here, the 0.150 meters. So we actually have the knowns and the unknowns here already done. Let's go ahead and do that. This is a sketch of the problem. You have the puck. You can see that the displacement is positive in this direction, so it's moving a positive displacement, and the force. So the motion and the force are in the same direction, which means that there's actual work being done on this puck. The other thing I'll want to point out here is that we've got the givens right here, mass, force, and displacement, and the unknown of work. Okay, so with our given and our unknown step done, all we have to do at this point is find the equation, the substitution, and the solution. So we can go ahead and do that here. The equation is going to be work equals force times distance. The substitution here is going to be the work is equal to 4.50 newtons. And we're going to multiply that 4.50 newtons times the displacement of 0.150 meters. Now, you'll see that the mass was actually extraneous information for this problem because the force was perpendicular to its mass, so we don't actually have to find the force of gravity. So we'll just multiply the force in the distance, the 4.50 newtons, by the 0.150 meters. And you'd get an answer of 0.675 for our solution here. Work would equal 0.675 joules of work. Okay, and again, that's in a positive direction because the force is in the same direction as the displacement. Okay, so let's go ahead and make sure that we cover energy now. So that was work, and work and energy are related. There's something called a work-energy theorem that basically states that when work is done on an object, the result is a change in the object's energy. So if you add work to something, you're increasing its energy. And the equation for that is right over here. Work equals your change in energy. And you have to kind of think about work as a way of transferring all of the energy that you're putting in from your force into the actual change in energy. So let's go ahead and take a look at how this can be applied to the energy of motion, because we have a specific name for the energy of motion. Okay, so this energy associated with motion is called kinetic energy. So it's right over here, kinetic energy. And Okay, so this energy associated with motion, kinetic energy, is represented with the equation that's located right over here, the translational kinetic energy. It's kinetic energy is equal to 1/2 times your mass times the velocity squared, where mass should be in kilograms and your velocity should be in meters per second. Real easy equation to apply, and we'll go over its effects on the change in energy here in the coming days. We also want to go over power, and power is the rate at which energy is transformed. So basically like the speed at which you're changing your energy. And the equation for power is right over here. It's power is equal to the change in your energy divided by time. We just discussed that work is equal to the change in energy, right? So we can say that power is equal to work divided by time. And this equation is going to become very important for us. Again, we're basically looking at this right-hand side where it says work divided by time. You also need to know that power is measured in watts, and that 1 watt is equal to 1 joule of energy transformed in 1 second. So instead of a meter per second, it's a joule per second. So let's go ahead and take a look at this example problem. It says that an electric motor lifts an elevator 9 meters, so that's going to be a distance, a displacement, in 15 seconds, so that's our time, by exerting an upward force of 1.20 times 10 to the 4th newtons. And they want to know what power the motor produces in kilowatts. So the units get transferred from one to the other just like they do with anything else. We just use the metric system here. And so we've got our displacement here, we've got our time, and you've got your force. And they want to know what power we have. So we'll put in the power there. Alright, so we have our knowns and our unknowns. Let's go ahead and show you a picture of what's going on with everything, but that would be the initial step where you show all the givens in the problem. So this is a sketch of it. You've got the change in y being positive upwards, so we're going to make up positive here. The displacement is up a positive 9 meters. The force is going up 1.20 times 10 to the 4th, which is basically 12,000 newtons, right? So 12,000 newtons of force going up. And we want to know how much power this elevator has to be able to lift that at in 15 seconds. So these are givens, this is our unknown. Let's go ahead and do the equation here. The equation is going to be that power equation, so it's going to be power is equal to work over time. We already discussed the work equation. It's just work equals force times distance. So we'll go ahead and fill in these two equations with the numbers we have. We'll substitute in our values. So we can't really do this equation yet because we don't know what the work is. We have the time and we want to find power. So we should finish this equation first. So work is what we're trying to find first. And our work is going to be equal to that 12,000 newtons. And we're going to multiply that 12,000 newtons times the distance or the displacement it traveled up, which is 9 meters. And that gives you 12,000 times 9, which is 108,000. Joules. And we'll take that 108,000 joules and we'll plug it into this first equation for the work, and we'll divide it by the time of 15 seconds. So let's go ahead and do that substitution step. It would be power is equal to the 108,000 joules of work. And we'll divide that 108,000 joules of work by the 15 seconds. Okay, so 108,000 divided by the 15 will give you 7,200. So our power is equal to 7,200 watts. But they actually want it in kilowatts. So if we wanted to convert that into kilowatts, that would be equal to just moving the decimal to the left 3 times. So it would be 7.2 kilowatts. So that would be our answer right there for our solution step. Okay, so sometimes in these problems you'll have to get the work first and then use that work to actually calculate for the power. Okay, this just shows the relationship between power and speed, and as you increase your speed, what happens to the output power. Really important you understand that to have a lot of power, you actually have to have a moderate amount of force and a moderate amount of speed. The place for this object, you see as their speed went down, the red line would represent the object, and as the speed went down, you'll notice that force went up, and right here in the middle area where you have a moderate amount of force and a moderate amount of speed, so like at about 400 newtons and about 2.6 meters per second, you see that's where you have the actual most amount of power here. Okay, so that's going to be important. Okay, so big main ideas are that you understand how to calculate work, that you understand that work is equal to the change in your energy, that by applying work to an object, you're going to be adding energy to it, which in this case, for the energy associated with the motion of an object would be kinetic energy. That kinetic energy can be calculated with that equation 1/2 mv squared. We also discussed that power is the rate at which energy is being added to a system, so it's the change in energy or work divided by time. And we went through some example problems for how to do that. There's some example problems down here, and you can go ahead and take a shot at answering those for me. You can turn those in Monday at the beginning of class, and we'll go over them and make sure that you have the right answers. Okay, that's going to conclude the initial introduction to work and energy notes. If you have any questions, by all means, please come and ask. I apologize for some of the pausing throughout the video. Had a lot of interruptions, and I wanted to make sure that I was able to finish. And that concludes the lesson for this Friday.